So as chemists, we need to be able to do balanced equations. And the reason for that is that a balanced equation tells us about the quantities of things that react together. Before, so in year 11, when you were asked to balance an equation, you probably didn't actually know why it had to be balanced. You just were told that we had to do it. Alright? The reason is that when you do a balanced equation, such as this one here, it tells us that for every one magnesium carbonate, it will react with two HCl or hydrochloric acid molecules. Okay? And we actually have a way of counting molecules and atoms and things called the mole, which we'll come to later on. If we don't have this balance, all of our calculations go wrong. We'd either put too much magnesium carbonate in it or not enough hydrochloric acid, and it wouldn't react completely. We'd wonder why we're left with a solid magnesium carbonate here, and we don't get as much carbon dioxide bubbling off as it might be. It doesn't seem like a big deal, but it is if, for example, you had an acid spill. Let's say you had a bacteria acid spill, so sulfuric acid. If you did that, you'd probably treat it with something around the home, like washing powder or something like that has a carbonate ion in it. When it stops bubbling, it stops reacting, but that's only if you use excess carbonate. By doing a balanced equation, you can almost predict roughly how much of that washing powder or baking soda, whatever you're going to use, is going to actually be needed to do it. And of course, I'm not going to go and work it out mathematically. That would be ridiculous. We're just going to chuck it on until it stops fizzing. But at least you'll have a fair idea if you want to check later that you can actually wipe it up with a cloth now. Alright? So we need to know amounts. This is about amounts. So how do I balance an equation? Okay, I'll just chuck one up here. I'm going to work my way through that one to see how we got here. What we might have been given is a problem like this. Balance this equation, HCl plus MgCO3. So just the first bit that I've got here. So let's say that was given to me and nothing else. Well, the first thing you have to do in the sequence is you actually have to work out what the heck is made. You need to work out the formula of the product. Okay, so step one, find the formula of the product. Don't worry about copying this, by the way. I'll take a photo and put it on the blog as well. You don't need to write unless you want to. Okay, so that's our first thing. I need to know the formula of the product. So what skills do I need to be able to do that? First of all, I need to know some general equations. I've got a carbonate and an acid, so I identify HCl as an acid. I identify magnesium carbonate as a special type of base called carbonate. And I know straight away that makes carbon dioxide and H2O. Now here I have an acid plus a carbonate, those two things are made. So I automatically put them on the right hand side. They're kind of a given. Not even kind of, they are a given. So I know my general equations off by heart. There's only a few of them. So that puts me in the right place already. The other thing that I'm really good at, thank goodness, and we all need to be good at, is we need to know how to work out the formula of salt. Alright? So we need to know how to do salt compounds. Because we're going to be working exclusively at this stage of the year with acid-base reactions. So it's a salt plus water, and sometimes it's a salt plus water plus carbon dioxide. So how do I do that? Well, for that I need to know my ions, and that links to what we did yesterday about the periodic table. Magnesium isn't over here yet. I know I've got it here, ignore that. It's not mentioned here, so I know magnesium must be important. So I've got down Mg. I then see that Mg is in the second group on the periodic table. So if it's in the second, it must make 2+ ions. So I'm going to write down its ionic formula. The other thing that's not over here yet, that is over here, is the chloride, or the chlorine. And chlorine as an element, or as an atom, is in group 17. So its ion, is the ionic compound, its ion must be -1. It's in the second last group. remembering the last group is amines and noble gases. So automatically I can see that I'm going to balance those two charges out, I'm going to need two chlorides, aren't I? Now this side is +2 and this side is -2, so they cancel out. You might be taught a little trick called drop and swap. It's a trick, it's not a reason. Okay? And it does indeed work. If the numbers don't match, then drop any number you do see, there's no number here, drop any number you do see, and put it over there. And this leads to it being NgCl. The 2's been moved to there, see that formula. Notice I've removed the charges. Now this is a compound, it is electrically neutral. It has no charge. So if I was to put the charges in there, I've now taken it from being correct to being wrong again. So I need to remove those charges. That's step 1. I've got those. Fantastic. Step 2 is start trying to balance it. And really this is just practice, practice, practice. So my little rule is to look for anything that is obviously not balanced. I'm going to remove my little push up here for now. Okay? So, one of the things I like to acid-base ones, I like to try and balance the hydrogens first. I find it an easy starting point. So I'm going to say balance, but I'm going to just give it a wee hint that we maybe start without hydrogen. It's a nice place to start. Because it often makes the rest of it fall apart. It's a bit like when you're doing simultaneous equations and maths and things like that. If you find the right equation to substitute in, boom, it just opens itself up for you. Same thing with balancing equations here. You can find the key, as it were, it seems to do it. So, I like starting with hydrogen. It's a really good place to start. So we're going to start with balancing the hydrogen. It's a nice place to start. So if I have a look on the left-hand side, there's one hydrogen here, in HCl, and there's 2 in H2O. Right, try that again. So, as I was saying before, we're going to start with the hydrogen and see if it balances. We see that there are 2 on the side, H2O means it's 2 hydrogens. But there's only one over here. Well, one of the rules is, we've already done the formula, we're not allowed to change them. You can't use the little subscripts and so on. They're done. We're finished with those. So the trick I often teach is change your pen colour. So maybe write the formula out in black, but balance it in blue, for example. So what we do is we go, well, if I need 2 of those, I must need 2 HCl molecules. So the way that I do that is I use a big number 2 in front of it, and sure enough, that works. Alright? It also gives me 2 chlorines though, so I better check that there's 2 chlorines on the other side. And sure enough, from doing our formula here, there's 2 chlorines. Then I just be a careful accountant, as it were, and check everything else balances. 1 magnesium, 1 magnesium. 1 carbon, 1 carbon. 3 oxygens. 1, 2, 3. So we're good. And I think that's the thing I'd probably stress to you the most, is be a careful accountant. Make sure both sides do actually balance. Don't just assume because you double the hydrogens, everything else works. Right, quickly going to go through a couple of others for you. Shot. So, we're going to do a very common one, H2SO4 plus NaOH. Thank you. Awesome. Okay, so this is a very common one, H2SO4, sodium hydroxide, and this is acid plus base. Acid plus base makes salt plus water. So I can put my water in straight away. Then I have to think about what my salts might be. Well, that's got H's, so they're pretty used up. That's got O's, so that one's used up. I'm not sure about this one. But what you need to be able to identify is that in sulfuric acid you've got the sulfate ion. So that's SO4 2-. Over here I've got the sodium, which hasn't been drawn over here yet, so that's Na+. And again, if I use a little drop and swap, put the number down there, I end up with Na2SO4. This one's a little bit trickier. There's 1, 2, 3 hydrogens on the left-hand side and 2 on the right. And it's hard to know what to do there. So my little rule about starting with hydrogen isn't actually going to work. If it's not easy to do, skip that rule. What else could I balance easily? Well, if I look at that, I actually reckon that sodiums look pretty easy to balance. So I choose the next easiest thing. If the hydrogens don't work, go to the next thing. So you can see there's 2 here. I need 2 here and I'm not allowed to change the formula. So I put a big 2 there. Well, actually suddenly that's done a really nice thing for me. It's given me 1, 2, 3, 4 hydrogens here. Which means I can get 4 hydrogens here very easily by having 2 water molecules. But then that's given me an extra oxygen. So I better go back and check. On this side I've got 1, 2, 3, 4, 5, 6 oxygen. On this side I've got 1, 2, 3, 4, 5, 6 oxygen. So I am indeed balanced. Right. Now, being level 2, not level 1, you introduce some new acids, and they're going to have really, really interesting formulas. One of them is ethanoic acid. And really, with this one, it's just a case of knowing how to balance it. This would be a very slow reaction. Calcium hydroxide or lime water reacting with ethanoic acid. Now, in acids that start with carbon, so what we call organic acids, the last hydrogen is actually the one they lose. In fact, the one right at the end. So this will become a thing called the ethanoate ion right below it. CH3COO minus, losing your H plus. Right. This is pretty straightforward. So again, we're going to look at acid plus the hydroxide, which is the normal base, which is going to make water. Calcium is a 2+ ion, so we're going to need 2 of this one I've written in red. So we're going to have to use brackets, because there's more than one atom in that ion. So it's going to be Ca bracket CH3COO bracket 2. Alright? Just to show you how I did that, you know, that looks a bit freaky. Ca was 2+, CH3COO was the minus, so I need that one twice. Which is why I put it in the bracket. Then balancing it, again, this one's actually a really nice one for the hydrogen. Pretty safe, you see. 2 there, 2 there. So it's looking pretty good. However, there's a bit more happening than that. So if we weren't careful, we'd say it's balanced and it'd be wrong. What you'll actually see is that there's 2 carbons over here, but there's 1, 2, 3, 4 carbons here. So this one's a really hard one to do. This is about as hard as it gets here in this internal. We can see that this iron has been used twice, so we must need twice as much of the acid. That gives us more hydrogen to be lost. We've now got 1, 2, 3, 4 hydrogens. So again, I'll double my water to allow that to be 4, and it's all balanced. That, as I say, about as hard as it gets for you guys this year in this standard.